Uh, Topic of today's lecture is amplifier with active loads, and the type of load which we are going to cover today is current sources as load. We know that in case of differential amplifiers we always prefer to replace these passive resistors by active resistors, and the advantage is that active loads require less area as compared to passive loads on silicon, and because of that we can save cost, and it's also possible to add more devices in that spare area, and that way we can add more functionality to the circuit, and that's why it's very useful to use active loads as compared to passive loads. In today's lecture we are going to cover these points. We will see various active load configurations, we will see what happens when we use current source as load, large signal analysis, we will see differential input conditions, equivalent circuit, and the equivalent circuit is used to find out voltage gain and input output resistance. We will see what happens when we take single-ended output instead of differential output, and finally we will summarize the discussion. First we will see active load configurations. So these are the most popular active load configurations. You are already aware about it. So diode connected loads, current sources loads, and current mirror can also be used as a load. In today's lecture we are going to cover this part, current source as a load, right? You know that in this particular configuration the gate terminals are connected together, and the gate terminal is biased with some gate voltage. This gate voltage will decide how much current will pass through the device. You can see here. So this device is used as a constant current source, so how much gate voltage, that decides how much current will flow here, and not only this gate voltage but this drain source voltage will also decide its configuration, so how it is working. So you can see if the drain source voltage is more than VGS minus VT, then the curve is almost flat, and ideally it is completely flat, and output resistance which it offers is infinite. Practically it is not infinite, but it's very high. It's this resistance which is offered by this constant current source is higher than the resistance offered by this diode connected load, and because of this high resistance we get this particular advantage for which we are using current source as a load. High resistance controls gain, and the gain, high resistance means we get very high gain, and this gain is higher than the diode connected load configuration, and that's why we are interested in this current source as a load. Now see what happens when we use current source as a load. This current source that can be modeled by a simple high value resistance, right? So they are offering very high resistance, and this resistance is actually the resistance between drain and source terminal of this device, right? In the same way this device will also be replaced by its equivalent resistance, that is resistance between drain and source. So this equivalent resistance of this current source is written like this, and you remember that in case of differential amplifier with resistive load there is RD term here, and now what we have to do, wherever that RD is there in the equation of voltage gain or in the equation of output resistance, that RD will be replaced by R naught. That's the only thing. So we have to focus on this R naught. This R naught will replace RD everywhere, right? Now if we talk about its large signal analysis, means what are the DC currents and DC voltages in the circuit. Input signal is same like other configurations, it's a differential input signal, and this differential input signal is split into two parts. So one half part is one input terminal, and another half part of this splitted differential input signal is applied to this second terminal, right? And if we talk about the DC currents in the circuit, so this ID1 which flows here, that is given by this equation. So it's very famous equation for current in the saturation region of a MOS device, and the same equation will give you current in this second branch ID2. But remember, ID1 plus ID2 is always equal to ISS, which flows through this branch, right? And the current in this branch is also equal to the current in this branch, because these two devices are connected in series. So that's why this ID3 is equal to ID1, and ID4, which flows through this branch, that is equal to ID2, right? So these things we have to keep in our mind. And as this device and this device, M1 and M2, are meshed device, in the similar way M3 and M4 are also meshed devices, right? Now after finding the output DC currents, let's see how we find out the output DC voltage. Output DC voltage means voltage at this terminal and voltage at this terminal. So voltage at this terminal will be given by like VDD minus voltage drop here, right? So this will be VDD minus VDS3, means drain source voltage of this device. In the same way, this VD2 will be VDD minus drain source voltage of this device, right? And the drain source voltages of these devices will keep on changing depending on your input signal, depending on the current in these branches. Now differential input signal. So many times we have discussed that it is very important to find out the highest differential input which we can apply here, because when we increase the differential input voltage, current in these branches, well, in one branch will increase and in another branch it will decrease. Okay, so if this, suppose the current is increasing here, the voltage here will decrease, and this voltage is increasing, this voltage is decreasing. So a situation may come when drain source voltage becomes less than gate source voltage, and then device can go into it can go out of saturation, right? That situation we have to avoid. So in order to keep these devices in saturation, M1 and M2 port, at least one device in saturation, so this differential input voltage should be within this range, right? So minus under root 2 VOV. VOV is overdrive voltage, and that is VGS minus VT. And we have seen in previous lectures that this equation can be written like this also, 2 ISS by beta. ISS is the total current which is flowing in this part, and beta, you know, is its K prime into W by L, and this beta is for these two devices. And the curve between this differential input voltage and output current is shown like this. And you know that when this differential input voltage is within this range, or you can say this range, both equations are giving you actually same range. So when the differential input voltage is within this range, then we get some response here, and once we go beyond this, then the current doesn't change, because current already have reached to highest value in one branch, and that way in another branch it will be 0, right? There is no further change in the output current. So this is the maximum limit of differential input voltage which we can apply to a differential amplifier. Okay, this range is again indicated with the help of this. Now equivalent circuit. See, this is the circuit of differential amplifier with the current source as load. Now we have to draw its equivalent circuit, and we will use the same principle which we discussed earlier in earlier lectures, that this point is considered as virtual ground, right? Virtual ground, because these branches are designed symmetrically, and whatever changes are there in the AC current or there, so the suppose this branch has some change, so this branch will also have a similar change, but only difference will be that they are opposite in sign. Means here if current is increasing, here the current is decreasing by the same amount. So because of this symmetry, this terminal is always considered as virtual ground, and all the voltages above this point are measured with respect to this. And this voltage here remains fixed, it doesn't change, because this remains fixed, so ISS remains fixed, so this point voltage never changes. So that's why it is considered virtual ground, and same concept we will use here to draw the equivalent circuit for this. So equivalent circuit is something like this. You can see this device is replaced by its equivalent circuit here, and this device is also replaced by its equivalent circuit here. This M3 is a current source, so it is replaced by its output resistance, and the same way M4 is a constant current source, and it is also replaced by its output resistance. and VDD is grounded because we are talking about the AC analysis. So for AC analysis, DC sources are grounded, and this point is virtual ground, so it is also indicated like a ground, right? And when this ground and ground, they are joined together because both are at same potential, this will come in parallel with this, and the equivalent circuit will be something like this. So V01 is this output, and this V02 is this output, and this is in parallel with this, something like this, right? So once we understand this equivalent circuit, now we can use this to find out important performance parameters of this amplifier. Like now we will see how we can use this equivalent circuit to find out the voltage gain. So first we will find out how much is voltage here corresponding to this differential input signal. Then we will see how much is voltage here corresponding to this differential input signal. Then once we know this voltage and this voltage, we will find the difference of these two voltages, that will be differential output voltage. And if we divide this differential output voltage by differential input voltage, which is this difference of this, then we can find out the voltage gain. So first see this output voltage, it will be given by this. So the current here in this branch, that is proportional to this input voltage, and that is GM1 into VID by 2, right? And this current flows like this, right? This. So the voltage here is this current multiplied by the net resistance. So the current is GM1 into VID by 2 multiplied by net resistance, means parallel combination of these two resistances. And this voltage is negative because current is going from like this, current is going like this. So this terminal is at higher potential as compared to this. It means this voltage is negative voltage. Same way we can find out voltage at this node, that is here you see this is minus VID2, and because of this current here is this, and this current will flow like this, and this current, remember, it is divided into two parts, right? So here also this current was dividing into two parts, it was going up like this. So here also this current is going like this, and then so the voltage at this node is this current multiplied by the net resistance here, right? So this is minus, and this is going from low to high, from this point to this point. So the voltage here will be given by this point, right? This equation. Now we find out differential output voltage, that will be VO1 minus VO2. So if you subtract this voltage from this voltage, what you will get? You see, you will get this part, right? So here we are writing R01 and R03 because R01 is equal to R02 and R03 is equal to R04, right? So when we are subtracting it, then this resistance, this part and this part, this is same. This GM1 is equal to GM2, right? So that's why all the, and VID is same, so all these are common. So finally we will get this, right? So if we find out differential voltage gain, so differential output voltage divided by differential input voltage, so VID will cancel and we will get this, right? So this is the equation of voltage gain. So you remember when we were using passive load, at that time this differential gain was given as GM1 minus GM1, of course, into R01 in parallel with RD. Now that RD is replaced by this this part, this R03, which is the output resistance of M3, right? It's output resistance of current source. Now sometime we try to represent this equation of gain in term of conductances only. Here this equation is written in term of resistances. So if we write in term of conductances, then it will be something like this. So because the net conductance here, that is conductance of this plus conductance of this, and that net conductance is inverse of net resistance. So this is net resistance, so inverse of net conductance is written here that will be 1 by GDS1 plus GDS3, right? And you know that GM is given by this equation and drain source conductance is given by this equation. So if you put values of these GM and GDS from here to here, you will get this one. So this is the equation of voltage gain in case of a current source as a load, right? Now we will find out output resistance. For finding out output resistance, what we have to do, we will connect a voltage source to the this point, right? And so this node will be connected to this, and this will be connected to this, like and this input will be grounded, and same way this input will also be grounded, right? So since the voltage here is 0, it's grounded, so current in this branch is 0, current in this branch is also 0, so there is no current in this branch and no current in this branch, because here input is 0 and here also input is 0. Now current in the circuit is flowing only because of this external source, and this current is divided into two parts, like this, okay, and then it is going here, and then again it is dividing into two parts, and it is flowing from both these two resistances. So if we want to find out total resistance here, so what we have to do, we have to find out this net resistance and this net resistance, and total resistance is net resistance of this left side plus net resistance of right side. Okay, so the output resistance will be this output voltage divided by how much current is passing through this side, and that can also be written like this. So this is the equivalent resistance of left hand side, and this is the equivalent resistance of right hand side. And now because this combination is in series with this combination, so we have to add them together, and that way we can find out the total resistance, and the total resistance will be given like this. You see this, because R01 is equal to R02, M1 and M2 are mesh devices, R03 is equal to R04 because M3 and M4 are also mesh devices. That's why we are writing it like this, okay. And if we represent it in terms of conductances, we can write it like this. So we have to find out net conductance, and inverse of net conductance is equal to the net resistance here, and that way we can write it like this. And we know GDS is given by this equation. So ID is DC current which is flowing in zero signal conditions. So then in that case this R out will be given like this. So it's R lambda 3, right? It's not lambda 2, it's lambda 3, okay. So that way we can find out the output resistance of the circuit. Now we see single-handed output. So sometimes it is important to find out parameters for single-handed output also, because in many applications instead of using differential output we use single-handed output. Single-handed output means we are taking output only from one side. So here for our discussion we are considering that we are taking output from this right side output point. So the input signal will remain same because it's differential signal, so that will be given by the same equation, and output signal is single-handed output. So we are talking only about output voltage at this node, and we have seen in the previous slide that output voltage here will be given by this. So this is the input signal which we are applying here, and GM is transconductance of this device, so that will decide how much current is there, multiplied by the net resistance on the right side branch. So from equivalent circuit also, if you remember, so we have output resistance of this device and output resistance of this device. These resistances are coming in parallel, right, like this, and here it's plus. So you can go back and you can see from those slides that voltage at this node is plus, because here we are considering that the input is negative half of differential input signal, and it's an inverter, so here we get output as a positive. And if you want to find out voltage gain, so the voltage gain, it's single-ended output voltage gain, so single-ended output divided by differential input. So this is single-ended output divided by differential input, so it means divided by VID will cancel, so it's GM by 2 and this. And if you remember, so this is single-ended output or single-ended voltage gain, so this S indicates single-ended. And if we talk about differential output gain, so differential output gain was differential output divided by differential input, and it was given by this equation, right? So remember these two gains. So this gain is for single-ended output and this is for differential output, right? And now compare them. So what you see, so in case of single-ended output, voltage gain is half of the voltage gain achieved in case of differential output, right? And the same was true when we were discussing a diode connected load, and it was exactly same when we were considering resistive load. So you have seen that whenever we try to take single-ended output, gain of amplifier reduces and it becomes half of the differential output. And I am repeating it again and again because in the next lecture we will see that the configuration which we are going to cover, that will give a little bit different kind of result. Now it's time to summarize our discussion. So what we have covered so far, so we have seen the equivalent circuit of this differential amplifier configuration with current source as a load. So this is its equivalent circuit, and we have find out differential mode out voltage gain, and differential mode out voltage gain is given by this equation if we represent this gain in term of output resistances, and if we represent it in term of output conductances, then it is given by this. So GM1 that remains same, so only change is that here we are representing it in term of net output resistance, and here we are representing this gain in term of net output conductance. And if you put the values of GM and GDS, so it comes something like this, right? And the differential output resistance, that also we have seen, so it's given by this. And if we represent it in term of output resistances, then it is 2 into R01 in parallel with R03, right? Now so what we have done so far, so in the previous lecture we discussed this particular configuration. In the present lecture we discussed this configuration where current sources were used as a load, right? So if we compare these two, what are advantages and disadvantages? Here you see this gate terminal is connected to VDD, and here it is connected to this a DC bias. So this configuration offers high gain as compared to this configuration, right? And the next lecture we are going to cover this particular configuration, right? Okay, thank you very much.